Now, there are not a lot of always, and what I mean by in physics, and what I mean by that is there are not a lot of statements where I can legitimately say always as part of the sentence. But here's one. Forces always come in pairs. Each force in that pair acts on a different object. So the direction of the forces in pair with respect to, that's the WRT, with respect to each other. For weight and gravitational force, those forces are always pointing towards each other. We will definitely be getting into more detail on that one. Just sort of laying out groundwork that we'll be referencing later. Direction of forces in pair with respect to the objects. Because in order to have weight, you need to have, let's just say, a planet and a body. The direction of those forces is always towards the center of the other object. Technically, center of gravity, center of mass, the center of mass of other object. I am being pulled downwards because that's where the center of the Earth, the center of mass of the Earth is. Likewise, the Earth is being pulled towards my center of mass. I'm being pulled down, I think the last time I got weighed, about 216 pounds of force pulling me down. Roughly 1,000 newtons of force pulling me down. I'm pulling up on the Earth the exact same amount of force. That is a concept that a lot of students have difficulty with. We don't notice the Earth moving or being influenced by me because the Earth is huge. It'd be like pushing on an elephant. You will push on the elephant with a certain amount of force, the elephant pushes back on you with the exact same amount of force. You're going to move because your mass is so much smaller. But that doesn't mean you're not exerting a force on the elephant. Let's make sure I didn't leave it. Let's see, requirement, direction. Oh, symbol. We'll throw the symbol over here. When talking about weight, the symbol I use is a lowercase w. If we're talking about the more generalized one that we'll get to in chapter 9 or 8 or some later on, F with a lowercase g. This is the general gravitational force. So when we get into the force diagrams, I'll be using W a whole lot. And I use lowercase w because uppercase W we are reserving for work, which shows up in chapter 7. Or watts, which also shows up in chapter 7. When it comes down to it, if you count Greek and our alphabet, upper lowercase, we basically have 100 symbols. So there is some overuse. Questions to hear? No? Oh, I thought you were raising a hand. All right, next one. Let's go with Carrie. Almost called you the wrong name again. Since Carrie mentioned the force between the chair and her, that is known as a normal force, N for normal. Now it's called normal because that's actually a math term. So let me throw it out to the group. What, in mathematics, what does normal mean?
What happened in the normal life?
No, not math people wouldn't go that way.
Healthy?
There's another word that you would have used instead of normal, but normal is a more generic term. Perpendicular. And the symbol for perpendicular is just basically an upside down T with a little box there in the corner. Just because writing perpendicular out, it's a nuisance. So that's all that normal means. The requirement is two objects touching. Any object you are touching at this moment, you are exerting a normal force on it, and it is exerting a normal force on you. Direction of forces with respect to each other. Normal forces are always, the pair of normal forces always away from each other. It's what keeps one object from going through another. I'm leaning against the board right now. The normal force is keeping me from falling into, I think, the bathroom. Direction of forces with respect to the objects, thus the name, they are perpendicular to the surfaces of contact. And then the symbol I use, and this messes some people up, but I use the capital Y for it. Now, why on earth would I use a capital Y for normal force? Where does it even show up? It doesn't. My high school textbook used a capital Y for normal force, and that basically stuck. That's why I use it. We also don't use capital Y for anything else, which makes it convenient. Now, some students, when they look at various resources, will see that I've actually, since high school, I've never seen Y used for normal force anywhere else. Some textbooks will use a lowercase n for normal force. So a couple other symbols that you might see elsewhere for normal force. Some might say, actually, let's put it over under symbols, a lowercase n. Some will use F with a subscript n. Please do not, whatever symbol that you use, please do not use a capital N. Capitals and capital letters, AL, right? Or O. OL is the building, AL is everything else. Do not use a capital N. Why not? Because capital N is used for newtons. It is the unit for force, and there's enough confusing things in physics that if you're using capital N for normal force, you might have an equation that looks like the normal force is equal to 3 newtons, and then those two N's do not mean the same thing. That's why I want you to avoid using capital N. We will run into something like this near the end of the course, but let's not do it earlier than we have to. All right. T for tension. Oh, questions before we talk about tension? Okay. The requirement, there must be a tight or taut rope, chain, etc. String. The pair of forces are always pointing towards each other. With respect to the object, it is always parallel to the taut, rope, chain, whatever you're using. The symbol I use for tension, I used to use a capital T. And the reason I stopped using capital T for tension is that there is a point in probably November when we have an equation that has tension and period in it. The symbol for period is capital T. And instead of using capital T now, and then for the next 2 months using capital T, and then getting to that equation and going, all right, we're now going to change the symbol we use for tension. So instead of doing that, the symbol I use is F with a subscript T there. If on the first test you use capital T for tension, I understand it, I don't take off for that, but just recognize that in class I will be using F with a subscript T for tension, just to avoid the nuisance later on. It's sort of conservation of nuisance. We're using too many letters now to save a hassle later, or we could take the hassle later and use something simpler now. F is for friction. Oh, and again, I did it once more. Any questions on tension before we talk about friction? All right, friction requirement. Two touching surfaces with desired relative motion. When we do the force diagrams, I will explain what I mean by desired relative motion in more detail. I guess, so if this table is perfectly level, this towel is sitting on it, or paper towels are sitting on it, there's not necessarily any friction. There has to be some desire for it to slide. So if the table were frictionless and it were perfectly level, this paper towels could just sit there and not slide anywhere. So that's what I mean by desired. If I tilt the table, now there's desired motion. The paper towel roll wants to slide down the table, so there is friction involved now. The direction of the pair of forces, they're sort of parallel but opposite directions. This is known as anti-parallel. And the direction of the forces with respect to the objects themselves, it is opposite the desired relative motion. And the symbol I use for friction is what I call the Baroque F. That's what I use for friction. Same symbol I use for frequency later. All right, questions to hear before we talk about flow? O stands for other. The requirement is there exists, this backwards capital E means there exists, this is just shorthand. There exists a force from an unknown source or from a source of no real concern. And what we're talking about there is the chair is holding each of you up right now. It is pushing upwards with a normal force acting on you. But if we don't really care, if all we care about is the fact that there's this upward force acting on you, that would be thrown into other. Or textbook problems are good for the first bit right here, the unknown source. A box has a 5 Newton force pushing on it. What's causing the 5 Newton force? Don't care. The direction of the forces with respect to each other are problem dependent. Actually, forces do come in pairs, but in the case of other, you don't draw the other one because the box is being, 5 Newton force is pushing on a box. What's causing it? I don't know, but there's some object over there where there's a 5 Newton force pushing back on it, but we don't care about that. So we only draw one of the forces. And the other one is acting on a mystery object or something we just don't care about. Direction of forces with respect to the object, it's problem dependent. The problem will tell you which direction it's moving in. And the symbol used, usually problem dependent, you can just, some generic letter. I'll put down problem dependent. I do recognize I've just thrown a whole lot of stuff at you. We're about to use this information. So any questions up to here before we start using it? All right, so let's do force diagrams. I'm going to take you through a series of force diagrams. It is going to end with a test level like problem. I will tell you right now, and if you look at all the old tests, all the first tests, there is a problem on there where you are doing a complex force diagram. It will be the same this semester too. You will do a complex force diagram for the test. The complex force diagram, I think the fewest number of forces I've had in the complex force diagram is 20, and the most, I think I've topped 40 at some point. But we're going to start out with the simple one. We'll slowly build our way up. The simplest force diagram, box falling. I have a planet down here. The hash marks on the side right here are indicating that this is not moving. I have a box falling. Little air streams there, even though we're ignoring air resistance for almost everything we do in this course, because air resistance is just way too complicated. This is to indicate that it is falling, not to indicate that it smells. or that hair is suddenly falling off. All right. Any question about what the situation is at the moment? All right, so when doing a force diagram, it might seem a little silly right now, but I want you to get into the habit of it. First thing I'm going to do is I'm going to draw my two objects. I'm going to draw the box, and I'm going to draw the ground. So to start out, this is the diagram representing the situation. This is where I'm going to do my work. And now we go to the checklist. First off, are there, of these 5 forces, is there any force that would definitely not part of this problem? For example, tension. Have we fulfilled the requirement for tension? So is there any tension in the problem? All right, that was easy. We got rid of one already. Other. Did I tell you that there's some mysterious force acting in this problem?
No.
2 down. Friction. Is the box rubbing against another surface or wants to rub against another surface? Another one down. Normal force. Is the box touching any object? Man, it's so easy. Just got rid of 80% of the problem right there. Weight. Is there a large object pulling on this box? Large object like planet. I got a nod from 1. Okay, I got a couple other subtle nods. People are really unsure on this one. You seem much more confident with the other questions. Do you think this box has weight acting on it? Still a little bit shy there. A little bit more enthusiastic nod on that side. Thank you, Rachel, for speaking up. Yours is the voice I heard. There is weight. Which way is the weight acting on the box? So I draw my arrow down on the box, and I put a little W there to indicate that it is a weight. So weight is acting down on the box, and so I draw my arrow down on the box. Now, forces come in pairs. They always come in pairs. So the other weight force is acting on what object? Yeah. Which way is it acting? And I put a little W right there. And you have completed the first force diagram right there. Done. It will get more complicated if you're feeling really confident right now. Notice that the pair of forces are pointing towards each other with respect to each other. And the force itself is acting towards the center of the other object. So the force acting on the box is towards the center of the Earth. The force acting on the Earth is towards the center of mass of the box. The biggest mistake I see students make here is they have it completely backwards. You're drawing the force, you draw the force on receiving object. In other words, this force right here that is pointing down on the box, this is the force coming from the Earth. The Earth is the source of this force. The box is receiving it. This force down here is coming from the box and acting on the Earth. So forces require 2 objects, one sending, one is receiving. You're supposed to draw the force on the receiving object. Some students will get it completely backwards, and their force diagram is indeed completely backwards of what it should be. I also want to point out the next one. I'll do what's called the free body diagram. So, questions before we do the next exciting installment. Try that again. The next exciting installment in force diagrams. Box on ground. The first thing to do is I'm gonna draw a picture of a box on the ground. And that's what it looks like. If you are an artist and want to get into a three-dimensional sketch, go for it. Now, I do want to point out that if it looks like my intention is to draw level ground, then it is level ground. I do not play the game of, oh, I can't believe you missed, it was at a 1-degree angle, that box would have slid. No, I don't do that. If there's an angle there, I will either state in the problem that there's an angle or a slope, or I will draw it so there's blatantly an angle. But this ground is supposed to be perfectly level. Now, next step is I draw the two objects. I'm not claiming that the box is in the air. All I've done is I've drawn the box, I've drawn the ground, because I need room to work. I would call having the direction of the arrows backwards is rookie mistake number 1. Rookie mistake number 2, not separating the objects, not giving yourself enough room. We have our checklist. Can we eliminate any of these forces? Okay, tension gone. Gone.
Other.
Gone.
We have
Pardon?
two. We have two forces.
Yes.
Weight and perpendicular.
Yeah.
Normal.
Yes, thank you. I was waiting for you to actually say it because there are a number of people, I won't say what the most common misnaming of this is, but it is normal. All right, so let's do weight. I feel like weight is the simplest one. Which way is the weight acting on the box? And it comes in pairs. Where's the other one? Ooh, so watch the preposition there. Not from the ground. On the ground. And it might seem like a huge nitpick on that, but if you can express it with the word on, that's how you draw the arrow. It's acting up on the ground, therefore you draw the arrow up on the ground. All right, so weight is done. All right, what about normal force?
Perpendicular.
It is perpendicular, so my surfaces of contact are like this, so the normal forces will be vertical. Which way is the normal force acting on the box? If the ground were not there, if suddenly there was a huge hole that appeared right underneath the box, what would the box do? So therefore, when the ground is there and the box isn't falling, which way does the ground have to be exerting a force on the box? Up. The ground's holding the box up. Normal force. If the ground is pushing up on the box, where's the other part of this pair? They come in pairs. Where's the other part of the normal force pair?
Ground? Into the ground? Downwards?
Okay, on the ground.
On the ground.
If you have walked in mud and you look behind and you see your footprints, it's this force right here that's causing the footprints. It's this force right here which is keeping you from sinking completely into the mud. So we're now done with the second force diagram. Just as a teaser, what's going to come up, we'll do this before the end of class, box on ground. Yeah, it does get that exciting. All right, questions on this before I talk about free body diagrams? Just because free body diagrams is a common term that you would see in a lot of other sources, and I just want you to understand the connection between free body diagram and what we're doing here. At some point, I'll figure out what colors show up best on video. All right, the free body diagram is incredibly similar to what we're doing. The only difference is instead of drawing boxes and ground, drawing the actual shapes, what they do is they reduce it down to a single point. And so they would do that and then write the word box. And you have a normal force acting up and you have weight acting down. Then down here you have ground with weight acting up and normal force acting down. This is a free body diagram. It represents the exact same thing. The only difference is I tend to draw two-dimensional objects, and that's a zero-dimensional object. And up through chapter 5, it really doesn't matter. I could have done free body diagram, but when you get to rotational motion in chapter 8, it really is helpful to know exactly where's the force being applied. And that comes from my engineering background. Now, I'm just trying to picture myself at various points in my life. At various points in my life, I would try to use as little paper as possible. It's not like it grows on trees or anything. So I would put as little space here as possible, and it would cause confusion. What I have seen, something like this, where the student did the force diagram on this. I have seen this. I look at that and I'm going, all right, does the student know what he's doing or not? I can't tell. So, I guess that's rookie mistake number 3, whatever number I'm on to. Another mistake that I will see, called rookie mistake number 4. I should codify it at some point. They'll do something like that. What I refer to as no man's land. Forces act on objects, so the draw arrows need to be on an object. Now, on a quiz or test, there's a certain amount of interpretation that I will sometimes do. So if it's something like this, and I see weight acting like that and weight acting like that, technically